Good morning, everybody. We are looking at section 1.6 today. That's going to be inverse functions. And remember, we've talked about functions before. So a function will take a set of values from one set and map it to a new set. So in this case, what we've illustrated right here in this first example, or first kind of illustration, I should say, is we're taking anything from set A, which only contains 1, 2, 3, 4. And when we put it into whatever our function happens to be, it sends those values to set B. And our function is given by f of x equals x plus 4. So when I put in 1, I get 5. When I put in 2, I get 6. 3 is 7. 4 is 8. And that's, you can see that I just take each x value and add 4 to it. So I'm taking something from set A, sending it to set B by utilizing that function. We can also, so then similarly there is an inverse function, and I know that the illustration that I'm using here, f of x equals x plus 4, and then f inverse of x equals x minus 4 is probably not the best example, but it does give you a better visual representation of what's happening, because every inverse function isn't simply a matter of just changing it from a plus sign to a minus sign. But in this case, in this linear function, it does work that way. And so if you'll look at our ordered pairs here, they are in reverse order of what we have in our given function. So what we have when we have a function and its inverse is the domain and the range flip. Okay, so the domain of our first function, let me label that just number 1. And then number 2. The domain of our first function is 1, 2, 3, 4. The range of our second function is 1, 2, 3, 4. And then the range of our first function is 5, 6, 7, 8. So I know you heard the phone ring and I got pulled away, and now I don't recall where I was at. But when we're talking about inverse functions, a function and an inverse function, you can think of it about they kind of undo one another. So if you take an inverse function and compose it with a given function, then what should result is the identity function. And the same thing is true as if you take a given function and compose it with its inverse, you should get the identity. And that's the two examples that you see right here. Here we have f composed with its inverse, and then here we have the inverse composed with f, and in both cases we get the identity function, which is x. For example 1, it just says find the inverse function of f of x equals 4x, and then verify that they are equal to, or that both compositions are equal to the identity. So to simply undo 4 times x, we would do division, and so our inverse, and we're going to look at a more mathematical approach to this, but right now we're just talking about it in terms of how it works as undoing. So 4x becomes x over 4. That's its inverse. So to compare to see if these are in fact inverses of one another, we will do the composition. First we're going to do the function f composed with the inverse. So I'll do that here in the pink. It's f inverse of x. So our f of x is 4x, and our f inverse is x over 4. So what this is going to look like is 4 times x over 4. When we simplify that, we do get x. So that in that direction, they are inverses of one another. Now let's check in the other direction where we compose the inverse with our given function. So now it becomes 4 over, sorry, not 4 over, it's 4x over 4, and these cancel and we're left with x. So in both cases it does end up being the identity function, and therefore they are inverses of one another. So the more appropriate definition of an inverse, if we have two functions f and g, f of g of x equals x for all x that are in the domain of g, and g of f of x equals x for all x that are in the domain of f. So this goes back to where the domain of the given function becomes the domain of the, or becomes the range of the other function. So under these conditions, the function g is the inverse of the function f, and the function g is denoted by this f inverse symbol that you see right here. The domain of f must be equal to the range of the inverse, and the range of f must be equal to the domain of the inverse. And if we look at example 2, we're just going to work out how can we come up with the inverse of this function, and we do that by composition. So if this function f of x equals 5 over x minus 2 is our given function, we want to test these other two to see if they're inverses, and the way we test that is through composition. So if we take f of f inverse, and we're going to use g of x as our f inverse for right now, this becomes 5 over x minus 2 over 5 minus 2. So we've replaced x with x minus 2 over 5. And now we need to simplify this. So the way that we simplify is through algebra, and we have 5 over x minus 2 over 5 minus 10 over 5. So we're rewriting that negative 2 as 10 over 5 to get that common denominator. And we get 5 over x minus 12 over 5. This will become 5 times 5 over x minus 12, because we have to multiply by the reciprocal when we divide by a fraction. And this gives us 25 over x minus 12. Since this does not equal x, this is not the inverse. With the second function, and I'll do this one in blue, we're going to do the composition again. We're going to do f of f inverse. Remember, we're assuming that that function that I bracketed there in the blue is an inverse. So we take our given function, 5 over x minus 2. We replace x with 5 over x plus 2. And then there's the minus 2 from our original function. So that's going to cancel. And now we have 5 over x, which is the same as 5 times x over 5. Our 5's cancel. We are left with x. So h of x is the inverse of our given function f. Graph of inverse function, that's easy to also take a look at, because the graphs are reflections about the line y equals x. And you can see that in this illustration here. We have some arbitrary function f of x, which is illustrated by the blue graph. I have the line y equals x illustrated there by the dotted line. And that red graph is the inverse. And so it is a mirror image of the blue graph as long as we reflect it over that line y equals x. And then you can see the relationship between the points A, B, and then how it flips around and the domain becomes the range and the range becomes the domain. So AB becomes BA, or vice versa when we're looking at these. For example 3, we're actually going to sketch these graphs and see how, I don't know why that's G, that should be an R. There's the phone again. All right, let's see. So we're looking at example 3. Sketch the graphs of the inverse functions f of x equals 2x minus 3 and 1/2 x plus 3 on the same rectangular coordinate system, and show that the graphs are reflections of each other. So we could, let's see, for the first graph, I'm going to do this one in blue, so that's f of x. We know that the y-intercept is -3 and the slope is +2 because it's a linear equation. And then for our inverse function, it's 1/2 x plus 3. So again, this case, our y-intercept is 1.5, and our slope is 1/2. So that's up 1 over 2, up 1 over 2, and we're going to get this graph right here. And if we wanted to verify that, the line y equals x looks like this. So that is a reflection about the line y equals x. We've just taken the graph of f, which is in blue. If we flip it over that red dotted line, it does in fact line up to be the purple graph. Now, sketch the graphs of the inverse functions. On example 4, it says sketch the graph of the inverse function f of x equals x squared. And what's important to note is this x is greater than or equal to 0. The graph of f of x equals x squared is a parabola that looks like this. But that includes negative values as well. This restriction, x greater than or equal to 0, means we only have this part of the graph. That's for all x greater than or equal to 0. Then we have the graph of f inverse, which is the square root of x, which looks like this. And we can see that those are inverses of one another. Again, if we draw the line y equals x through there, it is a reflection about the x-axis. One-to-one functions, that's another property that we want to be able to utilize that pertains to a given function. If the function is one-to-one, then the function does have an inverse. And we can graphically verify whether a function is one-to-one graphically by using the horizontal line test. And all that says is a function f has an inverse function if and only if. So just if I haven't used this notation before, IFF is mathematical notation for if and only if. So a function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. So thinking about our previous example, if we did not have the domain restrictions on x squared, if I draw a vertical or horizontal line through this graph, it intersects it at 2 points. Because it intersects it at 2 points, x squared itself does not have an inverse. But when I restrict the domain to all the x values greater than 0, where it looks like this, if I draw a horizontal line through that, it only intersects at 1 point. That's the horizontal line test. And if a function passes the horizontal line test, that function is considered to be one-to-one. So looking at these two tables, we have x, and our given function here is x squared. So when I put in -2, I get 4, -1 is 1, 0 is 0, 1 is 1, 2 is 4, and 3 is 9. That all makes sense. We substitute those x values in, and it generates this column of y values. If I flip those two columns, you can see that I have that in this table right here. So now my y values from the previous table become my x values in this table. And then my y values my x values in the first table are now my y values in the second table. The reason we do that is just to illustrate right here. I have 4 going to 2 different values. And whenever you have that, when we talked about definition of a function, because this function is not one-to-one, it does not have an inverse. And now I'm not going to read through each one of these steps. I'm just going to walk you through it with examples 5 and 6 so that you can see how to algebraically, this is what I really want you to pay attention to in these notes, how to algebraically find an inverse. The first thing that you want to do is take your function notation and replace f of x with y. So we have 5 minus 3x over 2. Then, to find the inverse of this function, we interchange x and y. So we rewrite this as x equals 5 minus 3y over 2. And now we take this new function that I have in red and we solve it for y. So we first multiply both sides by 2. Then I will subtract 5 from both sides. And then divide everything by -3. That becomes my inverse function. So if I wanted to write that in the correct notation, it's f inverse of x equals -2x minus 5 over 3. And that's how you find an inverse function algebraically. And like I said before, this is what I really want you to focus on. When we look at example 6, we rewrite it as y equals the cube root of x plus 1. We're going to interchange our x's and our y's. So to solve this for y, the first thing I do is cube both sides. So this becomes x cubed equals y plus 1. Subtract 1 from both sides. And there's my inverse. And then writing it in the correct notation. And that should be it. Yep. So there's your homework problems. For 1 through 4, it says show that f and g are inverse functions algebraically and verify using their graphs. You can verify that if you want to using the graphs. And all I'm simply asking you to do there is if you have a calculator, type it in. Make sure that they look like reflections about the line y equals x. If they don't, then they are probably not inverses of one another. But what I'd like for you to do, though, is when it says to verify that they're inverses algebraically, that goes back to what we did up here in example 2, where we took a function and did the composition. Really, we just want to look at what is here. You take the two functions, put one function inside the other. If you get the identity function, they're inverses. If you don't get the identity, they are not inverses. So that's what you're doing from 1 through 4. And then for 5 through 13, that's going to be exactly like what we did with examples 5 and 6. Rewrite the equation, solve it for y, you generated your inverse. So I hope that this is not too difficult. We're starting to wind down our first unit. You guys will be taking an exam probably next week if I'm not mistaken, but we'll have to look and see. If you have questions, let me know, and I hope everybody's doing great.